Hello, everyone. I think we can start. We are in the closing session of Second International Conference on Photovoltaic Science and Technology 2020. Thank you very much for joining this session.
Engin Hocam sesim geliyor.
Yes, I can hear you.
Engin Hocam, we are starting at a few minutes later. Please
okay.
Wait for our notification, and after that we'll we'll notify you about the beginning of this session.
Okay.
Please wait for our reply.
In a couple of minutes we can start, huh?
Yes. Okay. We will notify you about this.
Okay, thank you very much.
Have a nice session.
Thank you very much. Okay, we can wait a little bit. 6 p.m.
Engin Hocam merhaba, Raşit ben.
Merhaba Raşit Hocam.
Ne var ne yok, nasılsınız?
İyiyim, teşekkür ederim. Sizler nasılsınız?
İyi, nasıl şeyde?
Yoğun bir konferans programımız.
Evet, sonuna geldik. En son sesine epeyce
çok güzel.
Yoğundu.
Çok güzel.
Katılım da oldu yani. 200'ün üstünde kayıt oldu.
Aslında çok güzel. Oo, süper. Pandemiyle maalesef her şey artık online oldu.
Evet, evet.
Dersler,
yani,
konferanslar.
bunun da avantajları var. Bazı avantajları oluyor bunun da zaman zaman. Ama tabii keşke yüz yüze hep birlikte olsaydık.
Yolculuk.
Daha iyi olurdu.
Keşke.
Katılanlar oldu. Biraz başlayacak mıyız hemen? Başlayabiliriz eğer zaman geldiyse.
Evet, saat 16-18. I think two presenter is here, Mustafa Latif from Muğla Sıtkı Koçman University, and second presentation from Mr. Kamil Okay is ready here.
Yes.
Maybe we can start a couple of minutes. We are waiting for the audience. Sometimes it's not to go through the Zoom entrance. These are the last session of this conference. Thank you very much for joining us. I am from Kocaeli University. My name is Engin Özdemir. I am in the Faculty of Technology, Energy Systems Engineering Department. Actually, I'm working on photovoltaics, but in power electronics. In our session, we talk about power electronics in photovoltaic systems. We have two presenters. We can start with first presenter, Mustafa Latif,
yes.
from Muğla Sıtkı Koçman University. The paper name title is A New Implementing Approach for Tracking Algorithm on Photovoltaic Systems. Mustafa, you have 15 minutes presenting, and then we have 5 minutes Q&A, question and answers. The audience can write the questions from the chat, and I can read the questions from Mustafa, and he will answer the questions. Thank you very much. Mustafa, you can start your presentation.
Good afternoon, everyone. I think my presentation has been already sent. It's pre-recorded. Hello, everyone. Mustafa Hassan from Muğla Sıtkı Koçman University. Our daily life are requested to operate at constant voltage irrespective of the output disturbance that may occur or the PV system considers as one of those applications. Based on this fact, this work involves a new implementing approach for tracking algorithm on photovoltaic system. Here is the outline for our work, which include discussing the varying of two of those operating conditions, which are radiation and temperature. Then we will discuss our proposed system. Then we will highlight the algorithm that had been implemented. In the end, we will conclude some of the recommendations and conclusions associated with our work. So let us get started. First of all, despite all of the evolution and development that the PV cell witnessed in the aspect of fabrications and manufacturing, but to this time it doesn't exist as a device or component in most of the circuit simulation platforms. To overcome this lack and shortage, we had designed a prototype to emulate this shortfall and fill the gap in this aspect. Based on both Kirchhoff current law and Shockley diode equations, the output current would be derived as we can see here. All of these equations actually had been quoted from this reference, Zakaria. Here is a sample of some research attempts to overcome this shortage. As we can see, okay, they simulate it as one current source represent the photocurrent in parallel with one diode, and even some of them they choose to simulate it with two diode and of course two resistors, as we can see here. And here in this work, we can see they went beyond that and they tested it with NBBT. But if we look closer, we can deduce that none of them take in consideration to simulate the case when the temperature or radiation are changing. Because most of articles and researchers, they had choose the easy path and went in changing the spice code for the diode. In this work, MS-X16 PV panel had took as our PV source. We choose E-Altian worked as a reference in the aspect of extracting the MS16 parameters for RS, reverse saturation current, R shunt, etc. Here we can see the IV characteristics which have been taken from the datasheet of MS16, and here the parameters, some parameters also taken from the datasheet, short circuit current, open voltage, etc. Here what we were talking about it. This block diagram represents building the MS16 PV cell from scratch to be available to be simulated in various circuit simulation softwares. In our proposed system, we can modify both of temperature and radiation by changing the potentiometer here for temperature and here for radiation. For temperature, it had a range from 25 till 65 series. Meanwhile, for radiation, it had the range from 200 till 1000 watt per centimeter squares. Of course, after doing some mapping process, we can get these values, as we can see here, like for temperature, for this case, it was 25, for radiation around 1000. Here, the output that would be extracted from our proposed system, our prototype. We can see here represent the y-axis the current and the voltage, here x-axis. Here, meanwhile, here for the power and here's for the voltage. We choose some values for radiation, the same thing for the temperature to simulate or to see the negative effect, as we can see for increasing the temperature. We choose another radiation value, which was 1000, to see the positive effect if we compare it with the case was before. The case which we have seen before, it was 200 watt per centimeter square. Here for proposed system, as we can see, it consists from keypad. Actually, for the keypad, it has two functions. First of all, choosing the desirable input voltage, and the second role is modifying it during running the program by pressing on hash to increase it by 1 or decrease, or pressing on start to decrease it by 1. Then we sense the actual voltage from the buck converter. Actually, of course, it had a range like up to 21. but it's a little bit, it's not a little bit, actually it's dangerous on the microcontroller, and of course it will damage it. So we have to use like hardware mapping based on voltage divider rule, and to change it to another range up to 5 volt. Then we would subtract it from the desirable input voltage. Then the error would enter to the PI algorithm, and then the output of the PI controller have a range from 0 till my input voltage from the PV cell. And since in microcontroller we have like the register that responsible in pulse modulation here in my microcontroller, like have 8 bits, so it means have a range from 0 till 255 integer value. So we have to map it, scale it from this range 0 to input voltage to another range from 0 to 255. This is done according or based on these equations. Meanwhile, for PI algorithm, like this is the continuous domain, our time domain, we have to change it to another domain, discrete domain, because of course I'm dealing with microcontroller. That's me, I'm dealing with discrete domain. Here's represent the mapping process. Actually, it's just depend on triangle similarity theorem. So we conclude this final equations represent the mapping process, right? It means changing the output from PI controller to another range duty cycle, as we mentioned before. Here for controller design, as it is known from the literature of PI controller, it's equal to Kp plus Ki over S. So as we said before, as I said before, since I'm dealing with microcontroller, I'm dealing with discrete domains, so I have to change it to a discrete domain. This process done by using trapezoidal, like we divided the response to triangle and rectangular, and then after some derivation, we find this final equation that had been implemented in my microcontroller. We can see actually the T, which represent the sample time, is something critical in my design. It was chosen as 15 millisecond. Here is the algorithm. Actually, I know it's a little bit look like complicated, but if we took it step by step, it would be a little bit easier. At the first, there is system initialization for LCD analog digital converter and keypad, and for a pulse width modulation for the output duty cycle, and timer 0, which is responsible for sampling time. It was 15 milliseconds. At the first, this part, it's responsible for choosing the desirable input voltage, as we can see, and if it's above than 15 or beneath than 4, it would get a wrong input and return and ask the user to enter a new desirable voltage. Then it would be displayed in LCD. Here, this part, it's responsible for modifying the desirable input voltage by pressing on hash or star, increasing or decreasing. Here, it's responsible for sensing the output voltage here and feed it to be subtracted from my desirable input voltage and getting the error here. Then here in this part, it's responsible for implementing the PI algorithm according to the previous equations, and then mapping it, and then send the duty cycle with by CCP1 pin with 30 kilohertz. Actually, this value is it's up to the designer actually for designing the PI parameter. All ANSI. Then just wait till timer 0 to be completed to complete my sampling time to be equal, then return again. Here's my proposed system. Actually, here we can see the microcontroller, the keypad, the PV cell, our prototype, and buck converter, and LCD. Actually, we tested with 8 volt here. For desirable, it was 8. My real was 8.08. It's look like 8, perfect response. For duty cycle, it's the output from the PI after the mapping, actually, after the PI controller, after mapping it. Here's my input voltage, here's sensing it after doing also some hardware mapping based on voltage divider to convert it to another range to be sensible by microcontroller. A0 to analog digital converter. Here is the bootstrap circuit, of course, as it's known from the literature of the MOSFET. to energize the MOSFET to work in on period, VGS must be higher than thresholding voltage. As it is known, of course, the output from microcontroller, if we track this cursor, it has a range from 0 to like on-off 0.5 volt, blue one. It had to be posted to another range to be higher than the thresholding voltage, the VGS I mean. So we posted to 36 by IR211 and it's worked perfect as we can see here. Here actually represent the final output for whole of my system. We can see the radiation yellow color for temperature. It has blue for output voltage, white for duty cycle, it's green, and for timing each square consists or represent 200 milliseconds. Here we can see here the duty cycle and here's the voltage. We can see the direct relation between the duty cycle and the output voltage, which is known, of course, from the literature of buck converter, and we proved it here because we can see like the output voltage track or chasing by duty cycle. Here we choose or we enter our desirable voltage to be as 8, then we increase the radiation as we can see here. So the output voltage had been increased temporarily here for this period, and the PI controller here showed itself by decreasing the duty cycle as we can see to recompensate the increasing in the voltage, because of course increasing the radiation, increasing the output from the PV cell, so the PI algorithm show itself to decrease the duty cycle and hence decreasing the output voltage. The inverse thing happen with increasing the temperature as we can see, and the process continues forever. Actually, during running my simulation, here for this period, the desirable was 8 and perfect tracking with even some disturbance for both radiation and temperature. And here it was 7 desirable, and here for this period, it was 6, of course, with some disturbance. Like I got perfect response, acceptable response here for 5 volt, perfect response. The same thing is with 4. So we proved it worked perfect, actually, my proper system. Here, some conclusions on future works. First conclusion, it's possible, as we saw before, to simulate the PV cell with a bare current source represent IPH and some blocks to emulate the Shockley diode equations, of course, and two resistance RS and R shunt. In this way, we can simulate various PV arrays in plate form that doesn't support the PV cell. The second thing, the system shows a good response correspond concerning the temperature and the radiation varying. Some recommendations or future work may be considered as a future work. Actually, to reach the optimum design point, it's recommended to use some microcontrollers that support high bit resolution, of course, for pulse modulation. I mean, the last recommendation or future work actually to overcome the analytical barriers that are associated with the assumption in deriving the transfer functions such as omitting or approximating the process and etc. It's recommended to use plates form such as a LabVIEW to extract the real transfer function that describe the whole system correctly. In another word, treated as a black box to extract the real transfer function to help me to reach the optimum PI parameter. And I'm ready if there are any questions. And thank you for listening, and I hope you had enjoyed.
Okay, thank you very much for your nice presentation, Mr. Mustafa.
Thank you.
Is there any question? I am looking for the chat, but I have some questions about that. I think you have some simulations. First question is about what is your simulation program that you used for these nice results?
For coding, or you mean for the system, the circuit?
Both of them.
For the coding, it was Micro-C, and for the simulation, the circuit was the Proteus.
Okay. You don't have any experimental results?
No.
Okay. And another question is, it is very important in a buck converter to define the correct L and C parameters. How did you
Yes.
define the LC parameters? And the second question is the PI parameters. It's very important, you know. How did you select the PI parameters and LC parameters for the buck converter?
Okay, if we start talking about the buck converter, of course, from the literature of the buck converter, there is some equations for the designing the buck converter, and I think I showed in the circuit in the presentation. It was about for all as I remember, it was 130, and for the C it was 120 micro, both of them. And for the PI controller, it's of course there are many ways to evaluate and get the PI parameter, like if we can return to the transfer function. Actually, there are some articles talking about transfer function, extracting the transfer function for both of the PV cell and buck converter. I use them as a base, but actually in real, I used trial and error method.
Okay, thank you very much. And another short question about the buck converter modes. You know, buck converters has two operation modes. One of them is continuous conduction mode. The other one is discontinuous conduction mode.
I was working in continuous.
You choose the continuous. You didn't consider the discontinuous mode, eh?
No, for according to the L and C, I was working in the continuous mode.
Okay, thank you very much. Thank you very much for your nice presentation. I'm looking for the chat. There is not any other question. Thank you, Mr. Mustafa, for your nice presentation. We are on the time, and we have second presentation from Hacettepe University, Mr. Kamil Okay. The title is Development of Prototype Management System for PV Systems. Thank you very much for your presentation, Mr. Kamil Okay. The stage is yours. Thank you.
I will make my presentation online, if it's okay for you too. So I can start it. Good evening, ladies and gentlemen. My name is Kamil Okay, and I'm a master's student at Hacettepe University. I am also an officer in the Turkish military force. I work on battery and energy management system for especially PV battery system. Today, I will give some information about prototype battery management system for PV system we developed. I will make my presentation in order as seen in this slide. I will start by giving brief information about my motivation to set this study out. Then I will talk about the methods I used while designing the system. I will continue with subcomponents of the system. Then I will show some experimental results. Finally, I will share the conclusions of this study. So we can start with motivation. Residential consumers are responsible for 26% of total Turkey energy consumption in 2010. Their contribution to green gas emission is considerably high. Using of solar energy sources for residential purposes is believed to impact positively to climate change. But as you know, due to intermittency of solar energy resources, there are some concerns on consumers' minds about the especially efficiency and usability of the PV systems. When we look at the power generation profile of PV and household power consumption profile, it is clearly seen that the household power consumption is low during the daytime, when PV is most productive. On the other hand, when PV cannot generate power in the evening, household power consumption is highest. So by connecting batteries to PV system, supply and demand can be matched. Besides, by selling excessive power to the grid, consumer can turn into producer. And also in the literature, they call it prosumer. Lithium-ion battery emerged as a favorite storage option on account of its high capacity and high energy density. This is why we select this type of battery in our study. But besides these advantages, the biggest disadvantage of lithium-ion battery is being very sensitive. Only with the appropriate battery management system, lithium-ion batteries can be operated efficiently and safely. Now I will tell you about the methods we used while designing the system. The composite system is shown on this slide. The main components of the system consist of PV system, batteries, and grid and load. In the designed battery and energy management system, there are subunits are measuring unit that measure temperature, current, and voltage, charging unit that charge batteries firmly, main control unit that provide main control of the system, balancing unit that control balancing each batteries, and state of charge estimation unit that calculates state of charge of the battery block, and lastly, data logging unit that save data of whole system. As a PV system, two series, two parallel connected 400-watt PV panels were used. And as the battery block, 353 watt-hour capacity lithium-ion block was created. When necessary, the 300 watt power supply was used for buying energy from the grid, and 24 volts bulbs were used for selling excessive power to the grid. As a household load, 24 hours programmable electronic DC load with constant power mode was used. When we look at the conditions and corresponding to these conditions, energy flow direction of the system will be: first, when batteries are empty but sufficient energy can be obtained from PV, PV charge the batteries and also meets the need of load. Energy flow will be in this condition: PV to charger, charger to batteries, batteries to load. In the second condition, when batteries become full and PV produce more energy than the load needs, then PV meets the need of load, surplus is sold to the grid. In this condition, energy flow will be PV to charger, charger to batteries, batteries supply both load and grid, grid for selling. In the third condition, when batteries are empty and PV cannot generate energy, at this time, grid supplies the need of load over the batteries. And energy flow will be in this condition: grid to charger, charger to batteries, batteries to load. In the last condition, when PV cannot generate energy but batteries has energy, batteries supply the need of load by themselves. And in this condition, energy flow will be only batteries to the load. Now I will try to explain BMS and EMS we design. In the designing BMS and EMS, depending on irradiance density and the status of the battery block capacity, I mean the state of charge of the batteries, power goes from the PV or power goes from the power source as a grid to the charger. The charger adjusts appropriate voltage and appropriate current for the battery block. The lithium-ion battery block can carry out the energy storage function as well as compensate the sudden high power consumption. The most critical function of the system is to always meet the power that reduces the household needs. Beyond this need, when there is excess power generation from PV, the excess is spent 24 volts bulbs that acts as a sale to the grid. To create the reduced household power consumption profile, the programming feature of the electronic load device was used. Two types of households have been identified. These are households where retired people live and where working people live. For each day of week, you can see it Monday to Sunday. At 15 minutes intervals, 24 hours profiles were uploaded to the electronic load. In this slide, you can see Friday energy consumption profiles of both households. The circuit designed to understand the working and charge-discharge principle of the lithium-ion batteries are shown on this slide. First, a single 18615 type of lithium-ion battery charging circuit was designed. Later, the similar circuit was modified to charge 3 lithium-ion batteries connected in series. After the experiments with these circuits were successful, the main circuits with BMS and EMS and slave circuits for 7 lithium-ion batteries connected in series were designed. You can see main circuit and slave circuit here. And then 3 more slave circuits were designed and created. 4 slave circuits were connected in parallel, so this way the capacity of the total battery block was increased. Finally, all this experimental setup was placed in the solar house at Hacettepe University, where I am in now, and test. In the most appropriate position under Ankara condition, PV panels are replaced outside, and the rest of the system is placed inside the building as seen on this slide. If you look at the results obtained from experiments, in the circuit design section, it was mentioned that the design was initiated with a single battery charging circuit. When the experimental results of this circuit are viewed, a single 18650 lithium-ion battery is charged at different currents. Currents and voltage data is seen depending on time in the graph. In the second graph, the state of charge was calculated using the ampere-hour counting method in the charging phase, using the same circuit. Next, there are graphs of three batteries connected in series charging circuit. Here, during charging, it's seen that one of the batteries went above the threshold level without balancing. The third battery is above the threshold. Afterwards, this problem was prevented by adding the passive balancing feature to the circuit. As shown in the graph, the circuit worked. Results of the main circuit and slave circuit shown with the last graph. By using the experience gained from the previous circuits, charging data of 7 batteries connected in series was good as expected. As you can see also, thanks to balancing method, none of the batteries passed the threshold. If we look at the behavior of energy and battery management system against reduced household consumption profile, in the first graph, the power change of household where working people live are shown in a black color during the day. You can see it here. As shown, blue and orange color, while batteries are charging from the PV. After the batteries were fully charged, as shown in the green color, the excess energy obtained from PV was spent on dummy loads as if it was sold to the grid. In the night time of the same consumption profile, the power needs was met by the batteries for a certain period of time. When the capacity of the batteries were empty, they were filled from the grid shown in a red color. You can see it here. And also, as they were charging, need of the load was always met from the batteries. In the second graph, the power change of household where retired people live. Like the graph above, the power intake from PV, the power purchases from grid and sale to the grid, charging, discharging power of the batteries can be viewed. During the daylight hours, in the retired household profile, the energy consumption is higher than, you can see here, than the working profile. It's just here. The retired people are at home in these times, so the sale of the excess energy to the grid is lesser. It's just here in the retired people. I will end my presentation by giving conclusion based on the results. First, in addition to having highest energy density, lithium-ion batteries are very sensitive. BMS is need to operate these types of battery in a safe working area. And second, in the residential sector, PV battery storage system is more efficient than PV alone system. This effect can be further increased with appropriate energy management system. And lastly, the people of household can be produce their own energy without harming the environment, as well as reduce the depreciation period of time by selling their excess energy to the grid. So this way, consumer turns into prosumer. Thank you for listening to my presentation, and special thank you to Hacettepe Scientific Research Project Coordination Unit for supporting my study. If there is any question, I can answer your question.
Okay, thank you very much, Mr. Okay, for your nice presentation and giving us very useful experimental results you have also.
Yes.
And congratulations for you.
Thank you, sir.
I'm looking for the questions. One of the questions is asking about the tilt angle. Does the author consider the tilt angle of the photovoltaic modules while installing their test system in the Hacettepe University?
Tilt angle is the appropriate tilt angle for the Ankara. It's 37 degree, and it's the appropriate angle for Ankara and on the Hacettepe in the solar house.
You worked in summertime or wintertime?
We do the best experimental result. We get the experimental result, especially in the summer times, and my study is still continuous. So I will get the experimental result for this summer. I mean winter. So I will do that. Yes.
The season is very important, you know, in the winter and summer times. Sometimes, especially, are you using a battery? It's very important to conclude with energy management and battery management system. Congratulations, thank you very much. And I have a question about that. Did you get what is your battery ampere hour or watt hour rates for your battery?
Its capacity of my battery is 253 watt hour capacity. It's
okay. Do you talk about the passive balancing? How did you balance the batteries? Did you put some resistors on it?
Yes, we use resistors, and when the battery is high, so we consume its energy on these passive on these resistors in the system. We control it.
Is it enough for lithium-ion battery, or did you touch the batteries and get the maybe temperature of the battery? Is it heat or cold? Did you think about that?
We measure each battery of the voltage, so we can the system can calculate the needs when the balancing is on or off. So it's we decide the resistor power and resistor measure with the experiments. So we can decide the measure of the resistor with experiments.
Okay, thank you very much.
You are welcome.
And maybe last question about how did you get some results for changing of the loads for the retired people or working people? Did you get all the home energy consumption? Did you get the data?
Yeah, exactly. We have the energy management data device, so we put it every device of the house, and we collect the data, so we reduce it with the real.
These are the real data. Okay, thank you.
Real,
nice.
but reduced.
I see.
Yeah,
Okay.
but real data, yes.
You get the real data from the
Yes,
actual houses.
In my house, I measure all the device and collect the data, so reduce it for our system.
Okay, nice. Thank you very much.
You are welcome, sir.
Okay, I think this is the last of this session. Thank you very much for your nice presentations for you, both of them, the other audience. We are at the end of this session, and I think we will close the contact with closing remark time. And this closing remark will be given by Professor Raşit Turan and Professor Bülent Akınoğlu. They are the chairs of this conference, and I would like to thank them for organizing such a nice conference and inviting me also. Thank you very much. Mr. Raşit Turan, the stage is yours.
Thank you, Professor Özdemir. We thank you for chairing this session and being with us in this conference. And now we have come to the end of our second Pvcon conference, which is going to be larger and larger in the coming years, we hope. I think we have completed this conference quite successfully in these very difficult days and under these dark conditions of COVID virus. I will give you some statistics about the conference. In total, we have more than 200 participants. There's an echo. Who is Fatih Bey? Maybe you close you turn off your mic.
Huh? Şeyde açık. Is it open in your computer?
Öbür taraftan açık.
On this side, I think on this side there's nothing, huh? Fatih?
There's an echo. Still, it comes from you.
O şeyi kapatın. Close this. O sesi kapatın bakalım.
Okay.
He says that it's coming from there.
Please turn off.
Orayı kapatın.
Hocam Pvcon Live açıksa kapatır mısın?
Pvcon Live, is it open in your...
Açık değil benim Pvcon Live. Pvcon Live açık. Bütün ben şeyi kapatayım yani.
Sadece Zoom'dan bağlanın hocam.
Geliyor mu şimdi? Okay, it's okay now. I think it's okay.
It's okay. It's okay.
Okay, good. So we have more than 200 registered participants, 205, which is a good number for us. In the previous case, we have a little bit more than this number. But due to the COVID virus, the motivation to attend such conferences has been lower. Nevertheless, we have a good number. I think we are very satisfied with this number of participants. And next time, probably in 2 years, or maybe next year, we haven't decided that if we are going to organize this every year or every 2 years, and we will announce that later on. And we had 12 keynote speakers. They have all attended and well disciplined, and they have made very nice presentations from different aspects of PV technologies. We had 62 oral presentation submission, 53 of them have been accepted, 49 of them have been presented. And we had 54 poster presentation submission, 48 of them have been accepted, 37 of them have been presented. So I think we are happy about these numbers. What do you say, Bülent Hocam?
Well, in fact, the numbers is quite good in these days, in this time. What I can say is, for all the participants, including all guests, keynotes, we are waiting them for the next Pvcon.
Yes.
Maybe next year or maybe in 2 years. That's the thing that I want to add.
Okay, I think there are many people who deserves recognition and also our thankful expressions. First of all, I would like to thank all contributors, presenters, poster presenters, oral presenters, and all other participants, session chairs, keynote speakers, and the organizing committee. Of course, most of the job have been done by Professor Bülent Akınoğlu. He deserves a big thanks. I should thank him. And also Emre Demirözen, he has been working for this conference for many months and days, and he has spent a lot of effort. And I am a special thanks to him. And also, I should thank Academic Congress. There is a team behind this organization at the Academic Congress company, which is supporting us in this organization. So I thank them very much. I thank you, all of them. And I thank you now who are still with us at this evening time. So thank you and see you next time, next Pvcon. So I hope we make this Pvcon conference the major conference of PV in Turkey as well as in the world, not only in Turkey. Our aim is to be to make this conference one of the most recognized scientific and technological conference on PV in the world. Thank you very much again. Thank you.
Okay.
Thank you. See you.
Okay.
Bye-bye.
See you.